Hi, welcome to the Euclidean Geometry 101 course. Part 3 in the chapter about triangles now. This time we will be discussing congruence in triangles and we will prove the propositions regarding the congruence cases. These are very important propositions that we will be using a lot in other proofs. So, congruency. In lesson 5 we saw a general visual method for determining it that is unfortunately completely unpractical to use in proofs. For triangles there are, fortunately enough, very simple tests to determine whether two triangles are congruent. We know that two figures are congruent if they can coincide completely. And we are certain they will coincide completely if all sides have the same length and all angles are the same. In the case of triangles, that would give us 6 values to test for, 3 angles and 3 sides. That is too much, however. It is easy to see that if you have, for instance, 5 out of 6 properties that are identical, the triangles will be congruent. We want to arrive at the minimum number of corresponding things between triangles for them to be congruent. The propositions in this lesson will show us that this minimum value is 3 out of 6 for general triangles. Though not every combination of angle and side will suffice. There are 3 combinations that will work, and each of those combinations gets its own proposition. The first combination, and thus the first case of congruency, is as follows. Two triangles are congruent when they have one side and the 2 adjacent angles of that side equal. This case of congruency is usually stated and remembered as ASA, angle, side, angle. The ASA case is one of the propositions that have been attributed to Thales of Milesius, a Greek mathematician. So, let's show this to be true. We have 2 triangles ABC and A'B'C'. We are given that BC is equal to B'C' and that angle B is equal to angle B' and angle C is equal to angle C'. We need to prove that those 2 triangles are congruent. Again, we make use of the method of moving one of the triangles on the other. We do this in such a way that BC coincides with B'C'. The point B will coincide with B' and the point C will coincide with C'. As the angles in B and C are equal to the angles in B', C' respectively, we deduce that B'A' lines up with BA and C'A' lines up with CA. So the triangles coincide completely, ergo they are congruent. A second combination that is sufficient for congruency is the following. 2 triangles are congruent when they have 2 sides and the included angle equal. We show this in a similar manner. The 2 triangles ABC and A'B'C' have AB and A'B' equal, and also BC and B'C' are equal. The included angles B and B' are also equal. We will prove the congruency by again moving A'B'C' on ABC in such a way that B'C' coincides with BC, B' with B, and C' with C. B'A' lines up with BA because angle B is equal to angle B', and therefore A' will coincide with A because B'A' is equal to BA. So the 3 vertices of the triangles coincide. This means that the triangles are congruent. This case of congruency is known and remembered as SAS, side, angle, side. A last case of congruency is stated as follows. Two triangles are congruent when the three sides are equal 2 by 2. We will be proving this in an analogous, though slightly different way from the two previous cases. We have two triangles ABC and A'B'C', and the sides are equal in pairs. AB is equal to A'B', AC is equal to A'C', and BC is equal to B'C'. The proof of the congruency starts by reflecting triangle A'B'C' and moving it in such a way as can be seen on the figure. We have the triangle A'BC. ABC and A'BC are now on both sides of BC. Now let's connect A and A double prime. The triangle ACA' is isosceles, as AC equals A'C. Now we know from the direct version of proposition 6 that consequently the angle CA'' is equal to CAA'. We now consider in an analogous way the triangle ABA'. This triangle is also isosceles and AB is equal to A'B. Therefore, for the same reason, angle BA'' is equal to angle BAA'. So the two triangles ABC and A'BC have equal angles in A and A' that are included between equal sides. And we know that this is sufficient for congruency. So A'BC is inversely congruent with ABC. But A'BC is also inversely congruent with A'B'C'. So ABC is congruent with A'B'C'. This case of congruency is known as SSS, side, side, side. In future lessons, we will note that a seemingly fourth case of congruency called AAS, angle, angle, side, or a side, an adjacent angle and an opposing angle, exists. But this actually is not separate from the ASA case, because it is the ASA case in disguise. But the discussion of this case will have to wait until we have seen the proposition that gives us the sum of the interior angles in a triangle. Other combinations of three elements of a triangle do not lead to congruency. For instance, the AAA, angle, angle, angle case will not work because the triangle can change size while keeping the three angles the same. It's like zooming in and out of a triangle. A process of zooming in or out does not change angles, but the length of the sides change. Another case that will not work is the SSA case, the side-side angle case. This little construction shows you that we will always have two solutions in this case. For the time being, this is the end of the discussion about congruency. We will return to this subject in future lessons on triangles. If you like this series, consider subscribing to my channel.